important issue that we need to be dealing with, because as humans we use power in everything in our day-to-day life, whether it's driving to the store to pick up groceries or even using a toaster. I learned about this as a culmination of a bunch of different resources, whether it was plasma physics textbooks or scholarly journals, Fuser.net, which is very helpful. It's a collection of a bunch of different backyard scientists who are all sharing their scientific data, findings, experiments, methodologies, everything, and we work together and solve each other's problems. So that was how I was learning about it. So I would first like to start out with the common fears of nuclear fusion. So obviously when everyone thinks nuclear power, they think of Chernobyl, in 1986 when hundreds of people were irradiated, a lot of them dying from some sort of cancer-related, obviously because of the radiation disease. And when I took a survey here in the high school of over 60 high school students, I found that over half of the students reported having negative feelings pertaining to the subject, and almost half, roughly 48%, said that nuclear power is too dangerous to be using. And then obviously, even just now I've gotten lots of blowing up jokes about people saying, oh, you're going to flatten Spencerport into a crater. But and then in the more scientific approach and political community too, people say that it's way too unstable, it's too dangerous, it's bad for the environment because of the nuclear waste that is a result of all of it. So with all of that said, I would like to take a very subjective approach to defining what nuclear fusion is. So fusion, put as simply as possible, is combining two light particles and smashing them together, creating one heavier particle. So essentially what you're doing is you're taking deuterium, which is an isotope of hydrogen, because hydrogen is normally just one proton, and deuterium is a proton with a neutron, so it's heavier than regular hydrogen. And you smash together two deuterium, and then they create helium-3. So two protons with one neutron, and normally some sort of emission just because of the high energy nature of it. So normally you either have a proton emission, you can have a neutron emission, or a gamma ray radiation. Or you can leave it as regular helium-3 and then recombine it back with deuterium and have more fusion and more neutron emissions. But generally the ultimate goal of fusion is to have neutron emissions. So how does that compare with fission? So fusion, like I said, is combining of two lighter particles, whereas fission is the exact opposite. You take a really heavy particle and you shoot a neutron at it and it splits apart, releasing a ton of energy in the process. So nuclear fusion is a relatively new problem. We first started really picking up on research in the 1960s when Professor Farnsworth and his assistant professor, who was named Hirsch, they started developing, similar to that, they started developing coils and vacuums, trying to play with plasma and densities. And ultimately that research actually ended up going to cathode tube rays, which it was in the old televisions. So old televisions actually stem from fusion reactor research. But it's a relatively new technology, and it's also very expensive to research. If you look at the tokamak fuser that's in Russia right now, that costs $14 billion to build, and it's just a big experiment. There's nothing we're actually getting out of this other than knowledge and advancements in fusion. And if you look at the ITER reactor in France, it's the same thing. It costs about $14 billion, and it doesn't really do anything other than kind of shed some light in this whole gray, unknown area of fusion. So scientists are currently working on solutions, but because it's so new and it's such a complex field, it requires interdisciplinary tactics of solving. You have to have plasma physics, you have to have engineering. It's very, very difficult to make advancements and innovations. So why do we do this? Well, it's the idea of unlocking the door to infinite energy. So if we do finally solve the fusion problem, we could have unlimited energy that's infinitely sustainable and infinitely expandable. So what I mean by that is that when we do solve it, we are able, and we do have fusion plants that work, is we can expand the fusion plants to output more power, and we can increase the efficiency. And once it does finally break net positive, people will be a lot more interested in funding that research, so it'll expand a lot more quickly. And it has the ability to power everything because it will be converted into electrical energy. And the bigger point here is that fusion also protects Earth's environment. So unlike coal, which you burn and then you get bad residues in the air and you can create global warming and all that, fusion power, the fuel for fusion actually comes from water. So in water there is a natural abundance of 1 in 6,800 deuterium molecules to regular water. And as a byproduct of fusion, because all the fuel is actually cyclically used, you don't actually have any negative pollution whatsoever. So it's entirely clean source of fuel and absolutely zero pollution for unlimited energy. So it's extremely attractive. So to really summarize fusion, fusion is not fission. Fission is very dangerous. It's breaking a big nuclei into smaller, and it's hard to control that. You can have meltdowns with fission. It's entirely possible. But with fusion, that is not possible. It's very safe. If a chamber were to break in fusion, the reaction would just instantly collapse, and there's no way it could possibly cause anybody any damage whatsoever. Fusion has the ability to replace all power and pollution from fuel to water, and it has the ability to improve, expand, as long as we focus our efforts on it, just like any other source of energy. And it does make sense that the ultimate source of energy would be the most powerful source of energy in the universe. If you think about strong nuclear force, there's nothing stronger than it, therefore that would, in theory, be the best source of energy. So, what I've acquired through this entire process of researching is I've had to learn quite a bit of plasma physics and electrical physics and nuclear physics and mechanical physics. Lots and lots and lots of physics. And a lot of that was just scouring really old textbooks, because a lot of colleges and the professors will put textbooks online. MIT does that. It's very helpful. That was where I got a lot of my information from. I also had a lot of machining and technical knowledge that I gained, because putting that together, I really had no clue how to do it at first. But when it comes to stuff like drilling holes through a steel plate properly, or insulating wires through a steel plate, or attaching piping with Teflon tape so that you have minimal air leaks, all that sort of nitty-gritty stuff was very helpful in advancing my machining knowledge. The other really important thing was industrial relations. So a lot of these parts are very obscure. They're impossible to find anywhere. And so I had to scour across dozens and dozens of suppliers all across Rochester, whether it was Klein Steel to get a properly fitted and insulated plate, whether it was Keenan specialty vacuum pump store, where I had to go find that one super obscure hydraulic fit to my vacuum pump. It was absolutely impossible. I went to Granger, I went to tons of different places, none of them had it until I finally came to that. So it was really a big scavenger hunt all across Rochester just to find parts. And then the last thing was tenacity, obviously, with all of that driving everywhere, and then everybody saying, no, we don't have this, go here, and then repeating that process hundreds of times. It's will breaking. And then the other thing is I've had lots of errors with that, whether it was with my transformer, I burnt a fuse and I try to replace it and it doesn't work, so I have to order a new one, which is another $70. And just lots of things don't work, but eventually I learned that if I can push through it, then I can make the impossible happen. So now I'm going to turn this on. I'm going to let it run because it takes a few minutes to get the vacuum down to an acceptable pressure. Properly vacuuming, currently it's about 5,000 microns, which is very, very, very low. If you think about 1,000 microns being at 1 torr, and there are 760,000 torr at regular atmospheric pressure, so that's extremely low currently, but I'm trying to get it lower just for plasma purposes. So essentially I'm creating the conditions of space in there. But anyway, so here's more of a sidetrack. This was done more recently. I decided to use some formula derivations with the measurements that I could properly get from there. And I did them all in this notebook. And I got some help from some physics sites online. And this is also what I was talking about with the physics knowledge I had gained. And then I converted So it did present a very unique challenge of trying to avoid multivariable calculus, because with that, when you think about a particle's position, the force acting on it can vary as its distance in the wire varies. So to fix that, I addressed it at only one specific point, so linear, so I had to avoid that, which is very good. So I'm just going to very briefly skim over this because it's difficult. But so I started, these are all the different given formulas that I collected from the internet and from my AB Physics reference table. So all of these are used, and actually I think there's a few that I forgot to put on there that were not used, but there's stuff like that drag force equation, energy, force, magnetic field strength, all that stuff. So first I started out tackling the electricity magnetism calculation. So I started with my equation for magnetic field, and then substituted in the proper variables of what I do actually have measured. And then, so this was the equation for magnetic field. I convert it into force, so multiplying by the I-L cross product B. Got it in terms of force, and then figured out the net force by adding the forces of the two different coils minus the force of drag, which is relatively very minimal because of how low the vacuum is. So I found an equation for F net, and then there it is. So then I converted the force into an energy by multiplying over distance. And then because I know that energy can also be equal to kinetic energy, which is 1/2 mv squared, I set that equal, solved all the way out until I got V, then plugged in stuff for the drag force equation, and then solved for V max. So this was a very happy moment for me, because this was the equation that I could use as long as I properly substituted in variables. This was my equation that I could use to find maximum particle velocity in the chamber. So these are all the measured values and values that I got off the internet, such as the mass, the deuterium, and cross-sectional area. I plugged all of those into the Vmax equation that I derived, and then found a maximum velocity of 216 million meters per second, which is roughly 2/3 the speed of light, which is roughly very accurate, because normally in fusion reactors it's about 1/2 to 2/3 the speed of light for particle equations. So that made me very happy knowing that I was roughly on the right track. And then just to check my work and to prove that I was conducting fusion in there, I plugged it into an energy conservation equation, in which I took my calculated velocity and the known mass of deuterium, plugged it into the conservation, and then found out that my calculated value was very, very close to the accepted value of the power of fusion. So the idea behind this was that the total kinetic energies before have to equal the total energy given out afterwards, so energy is conserved. And that was just very exciting to see that my calculations were valid, one, and that 2A actually did conduct fusion. So this is mathematically proving that my project does work. So this is a picture, this is the best picture I have of it, but this is a picture of very, very low pressure. I got it down to about 1,000 microns, which is 1/760,000th of an atmospheric pressure. And what you see here, this is actually plasma surrounding the inner and the outer bit. And this is essentially the same setup as the sun, where in the sun you have force of gravity that pushes everything towards the very center, and that's where the collision happens. Whereas in this, instead of the gravity of the sun, because I don't have that at my disposal, what I do instead is I create tremendously strong electromagnetic fields, which is why these wires are there, because I can send really high voltages to them. And then that forces the concentration point of collision at the very center, similar to how the sun works. So it's possible to put the shade down. It's difficult to see the plasma. Right now what I'm doing is I'm just going to create some plasma. I probably won't get a folder like that. I'll probably just do a condensed ball, but you'll still get to see plasma, which in there it's very difficult to calculate. It's anywhere from 30,000 to 100,000 degrees. Very hot. Check the pressure. Yeah, all right. Right about ideal pressure. Sorry about that. reaction of